are in Chapter 3 of Generalized Linear Models with examples in R. And we're on question 319. And so here's the question. It's a nice short answer today. So we have a study of urethral length and mass of various mammals, expected to find isometric scaling. So that is proportional relationships being maintained as the size of the animals increases. Okay. So we're going to look at the data set called urinationL right there. Then to test the postulated relationship, the isometric scaling relationship, where length is a function of mass to the third and some proportionality constant k. All right. And so by using a transformation, fit an appropriate weighted linear regression model and test the hypothesis using both a t-test and an f-test, interpret the model. Okay. So I think that the potentially tricky part here is understanding what the transformation needs to be. All right. I mean, it's staring us right in the face, but it can, if you're not, real familiar with looking at these things, it might just, slide right past you. So what we want to do, so notice that this really is a linear model here, okay? And here, it's like a linear model without an intercept, right? And then this would be like the beta coefficient that we're trying to estimate, and then our predictor variable would be mass to the 1/3 power. So the transformation is just to transform mass to the 1/3 power here, okay? So, and then we will estimate k. That's going to be the coefficient that we're looking for, all right? So we need to install and load the GLM's data package and call up the urinationL data set. And then I'm just going to transform the mass variable, calling it m.1_3. So I'm just going to transform it by raising mass to the 1/3 power, okay? And so we'll see what this all looks like. So here's my new variable. Okay, I've transformed mass, and now it looks like this. Okay, and now we just build the linear model, right? We have length being regressed on m1 over, or m to the 1/3 power here. Okay, so I have that, and so we're supposed to test this with a t-test as well as an f-test. Okay, so I'm just going to rely on the output from the summary function. So so it's not very specific what we're supposed to apply the tests to. We might apply it to the t-test just to the intercept and the f-test to the whole model, for instance, and that's what I'm going to assume is taking place because the f value is just t-value squared, so we implicitly already have the t-value. Okay, and then we have the f statistic based on the whole model here. Okay, and so we see that looks pretty good. And so I thought it would also be interesting to plot these. So first I will plot length as a function of 1/3 power of mass. And then I will plot length as a function of mass, and then draw a line representing, our formula. K, here's K, the coefficient of the model, times mass to the 1/3 power, right? And so, so here's the first one. So here's our transformed mass variable, right? So we see a nice apparently linear relationship. May be a little bit heterogeneous with the variance as we get to bigger values, but we'll ignore that for now. And then here is the raw data, and notice what has happened here with the curve. When we plot the curve as as our transformed mass variable, and it makes this nice fit to the data. Now, as I started this video, I realized that we may be intended to set the intercept to 0. And in fact, that would make sense because we would imagine an animal of 0 mass would have 0 length of their urethra, right? And so I'm actually going to do that here on the fly. I think that the appropriate coding is just to put a 0 out there. Yeah, so now we have the coefficients without the estimate, okay? And now we just have one coefficient is 1. And so let's plot that and see what that looks like. Okay, nice. Okay. So anyway, I think I will leave it like that without the intercept and call it good.